Everyone, my name is Petro Artemchuk. I am a PhD student in the Department of Physics at Oakland University, work under the supervision of Vasilij Berkevich and Andrei Slavin. And today I would like to tell you about stabilization of a nonlinear spin wave bullet mode in the presence of a hot magnon gas. So motivation for our research comes from magnons, specifically different things we can do with them in magnetic samples. In particular, we consider magnetic sample of a thin film geometry, which is in plane magnetized. And if we consider magnons propagating in different directions, the spectrum of magnons will look like this picture on the right. And if you consider magnons propagating along the magnetic field, their spectrum will have a feature which is 2 minima at the non-zero magnitude of a wave vector, which is very important for magnon behavior. And there are a lot of different things we can do with magnons. So one of them is creation of the Einstein condensate of magnons, which is briefly mentioned in this picture. So what is actually happens, we through different means we add additional magnons to the system. Then as they thermalize, high energy magnons create a lot of low energy magnons. They accumulate at the bottom of the spectrum, and if the critical density of magnons is achieved, well, the Einstein condensation occurs. Second interesting phenomenon we can observe is the nonlinear bullet mode. So this bullet mode is nonlinear, is similar to solitons mentioned in the previous talk, and this mode is very famous for being strictly localized in space and having frequency which is lower than the minimum frequency of the magnon spectrum. So Bose-Einstein condensate of magnons can be created through different methods, and one of them I'll briefly describe here is a rapid cooling process. So what happens is first we heat the sample. In this particular experiment, they apply 120 nanoseconds heating pulse. The sample is heated and additional thermal magnons are created. And the second step is rapid cooling, which is possible due to sample being a very thin film. And at this step, actually, thermalization of additional magnons occurs, which leads to accumulation of magnons at the bottom of the spectrum. And this accumulation, it leads to increase of chemical potential of the magnon gas to minimum frequency of the magnon spectrum, which is important feature of the Einstein condensation of magnons. As for nonlinear bullet mode creation, it's usually created, for example, through spin torque or spin current pumping. And for example, in this particular experiment, of the increase the current passing through multilayer structure, first only usual ferromagnetic resonance mode is generated, and the frequency is decreased with the increase of current due to increase of amplitude. And then at a certain point, due to nonlinear effects, this nonlinear bullet mode is generated at a lower frequency than the usual resonant one. And then the question arises, so what will happen if you create these two phenomena together in a single sample? So what will happen and how will they interact? Actually, this experiment was done by people from University of Vienna and University of Kaiserslautern. So what they were doing, they were heating the sample and generating the nonlinear bullet mode at the same time. And as we can see in one case, at a certain heating pulse, we see that the bullet mode fades quickly due to its significant nonlinear damping, while in the other case, at a higher temperature heating pulse, the nonlinear bullet mode has significantly greater lifetime. And then the question is, why does it happen? And our aim is to explain this phenomenon. So to explain this, we use a simple model that is based on kinetic equations, and this model was first proposed in this paper, which is dedicated to generation of condensate of magnons using rapid cooling process. It uses kinetic equations of this form, where we consider density of magnons, density of states for magnons. We consider influence for magnon scattering. We consider damping. We also consider influence of equilibrium population of magnons. And in this model, we consider interaction between magnons, interaction of magnons with the lattice of variable temperature, and interaction of magnons with a nonlinear bullet mode. So we consider interaction in the form of magnon scattering, and the first type of such interaction is just thermalization of magnons. And the second type of interaction is interaction of magnets with the bullet mode, when one of the magnets goes to the bullet mode and the second one stays in the magnon gas. So we start from simple simulation where we do not hit the sample, and we see that the population of magnets at the bottom is quite low, and the bullet mode lifetime is roughly 20 nanoseconds. Then we complicate the situation. We hit the sample to 440 Kelvin, and we observe accumulation of magnets at the bottom of the spectrum, and we observe the increase of the bullet mode lifetime to roughly 146 nanoseconds. Well, okay, so we got the stabilization of the bullet mode, but how does it depend on the heating temperature? So we look at it and we see that this dependence of the bullet mode lifetime on the heating temperature, it has a threshold behavior. So basically, if your sample is hot enough, the condensation of magnets will occur, Bose-Einstein condensation. But so far, our simulations, they just kind of reproduce the results of experiment. They do not say what exactly is happening and why. Why exactly it's possible to stabilize the nonlinear bullet mode. And to understand this, we need to go a bit back to basics of phenomena we consider. So first important feature in the creation of Bose-Einstein condensate of magnets is that the chemical potential of a hot magnon gas increases to the minimum frequency of the spectrum. And the second important feature is the frequency of the bullet mode is lower than the minimum frequency of the spectrum. And in this case, we get a situation similar to inverse population of states in lasers, but in this case, the system has inverse population not in a sense of real populations, but in a thermodynamic sense, when the chemical potential of a magnon gas is greater than the frequency of the bullet mode. So in this case, the bullet mode can be amplified with a certain amplification rate, which depends on the difference between the chemical potential of the magnon gas and the frequency of the bullet mode. And thus, we propose the next stabilization mechanism. That first, thermalization of hot magnon gas during rapid cooling leads to increase of the chemical potential of the gas. As this chemical potential increases, it at a certain moment exceeds the frequency of the nonlinear bullet mode, and this makes the nonlinear bullet mode amplification available. However, this sounds good, but we forgot about something. So we forgot about the damping of the bullet mode, which is quite significant and nonlinear. So what happens actually in real life is that the damping, it works against the amplification rate, and it increases the level of chemical potential to be exceeded to amplify the bullet mode. So basically, there is a certain critical value of chemical potential that must be exceeded, and it depends on damping. And this value can be easily calculated. So we calculated it, and here you can see the final results. In the first case, the heating temperature is less than the critical temperature for amplification. And we see that the chemical potential of the magnon gas, it increases, but it never exceeds the critical value. And the bullet mode lifetime doesn't increase much. It's roughly 21, 23 nanoseconds. On the other hand, if the heating temperature is greater than the critical heating temperature, like here we heated the sample to 440 Kelvin, so we see with time the chemical potential of the magnon gas increases. At a certain point of time, it exceeds the critical level. Thus, the bullet mode is amplified, and the bullet mode lifetime is roughly 146 nanoseconds. And this is not even end of the story yet, because what we can think of is that there are different types of low frequency modes exist. For example, there's edge mode, which is also has quite low frequencies, and also gyrotropic mode, which corresponds to rotation of a vortex core in a nanodisk samples. So to continue this research topic, we want to generalize this approach to other low frequency modes and to see can this be done with them as well as the bullet mode. And in summary, We say that when chemical potential of the hot magnon gas is greater than the bullet mode frequency, the bullet mode will be amplified, and this can be used to increase the bullet mode lifetime. And we expect this phenomenon to be generalized for other types of isolated low frequency modes. And that's all for now. Thank you for attention.
Thank you very much, Petro, for a very nice talk. I don't know if there are any questions.
Can I ask?
I'm going to ask. Oh, yeah, go ahead, Alberto.
So, Petro, this is a bit off what I do, but so if you consider an ultrafast laser pulse, you create a very excited magnon system. I work in ultrafast systems, right? Mm-hmm. You can create a high energy population of magnon modes. So this drives your system away from the Bose-Einstein picture. How this relates to this? So I'm trying to understand what is a low frequency mode for you when I compare it to like a system that is ordered and I populate some magnon modes after an excitation.
So what do you ask? You ask how to compare it to high frequency excitations.
So you consider a low frequency excitation something that is within the Bose-Einstein? This has to be is this in the Bose-Einstein condensate phase?
Yes, basically they're created in the same sample, in the same kind of real space kind of point.
Okay.
So they coexist. So that's why they can interact. Yeah.
I understand. I see. Okay, then I was just mixing up concepts. Thank you.
No problem.
Well, thank you again, Petro. We don't have more time for questions, but maybe we can hang later at Gather Town.
Okay.